Okay, and welcome back, ladies and gentlemen. In this video, as you guys can probably read the title, it says we're going to talk about more boundary conditions. Yep, that's right, ladies and gentlemen, as if one video was not enough. And the fact that I'm making more than one video should tell you guys that the sheer importance of this topic. A good understanding of boundary conditions is going to make your life so much easier in a transport phenomena class. Trust me when I say this. If you have a good understanding of boundary conditions, some of these problems are going to be cake. Let me draw that for you. All right. Some of these problems are going to be cake. All right. Enough drawing lessons, more transport phenomena. I mean more boundary conditions. Here, as you can see, my poorly drawn figure. I am not an art major. This is my poorly drawn figure. I have laminar flow. I have laminar flow in a horizontal pipe. Some of you already know this. Some of you who have read ahead and done their homework. Now this is the Hagen-Poiseuille. I don't know how to spell Poiseuille, so I'm just gonna trust my memory. I'm gonna edit that in the comment if that's wrong. Hagen-Poiseuille flow. All right, this is going to be a simple application of the Navier-Stokes equation. This is one of the main applications of Navier-Stokes equation. I'm just going to call it the NS equation, the Navier-Stokes equation. Okay, I'm not going to go over the physics of this problem. I'm just going to go over the governing equation and the boundary conditions. And the governing equation is right here. The governing equation right here. This right here is a ordinary differential equation. This right here is a second order ordinary differential equation, and it's second order with respect to radius. All right, keep in mind we're working in cylindrical coordinates. We're working in cylindrical coordinates here, ladies and gentlemen. Okay, so once I integrate this expression, I'm gonna have to integrate this twice. Since it's a second order ODE, that means I'm gonna have to integrate twice. And when I integrate twice, that's gonna spit out, this double integration is itself gonna spit out two constants. All right, I need to evaluate those constants of integration. And how am I gonna evaluate that? Well, that's where my boundary conditions come into play. Once I'm at this spot, once I have my constants, in order to evaluate those constants, I'm going to use my boundary conditions. And in this case, it's going to be two boundary conditions. Why two? Because it's a second order differential equation, okay? And those boundary conditions are going to be in the radial direction. Why? Because the variation is with respect to radius. But that's it. Let's go back to the image for a second, and let's see, the boundary conditions are going to be physical. Like, you have to physically look for the boundaries of the region of your domain. You need to look at the boundaries of your domain. So in this case, my velocity, my dependent variable is a function of the radial distance from the center of pipe. Here I have the center of pipe, and r is just the radial distance. Okay, so as you can see, my points of interest are the center and r equals r, the radius of pipe. Okay, r sub pipe. So the radius of pipe, this capital R equals capital R, and r equals 0 is where the interesting stuff is happening. And I'm gonna go ahead and just tell you what's happening there. I'm not going to go over the how and why. That's going to be covered in a separate video, hopefully soon. Okay, so the boundary conditions in this case, the boundary conditions, the interesting stuff in my problem that's happening. All right, so at my velocity at r equals the radius of pipe, so basically at the wall, the fluid velocity is going to be 0. Why is that? Just to give you a hint, no slip condition. What is no slip condition? We're going to go over that pretty soon, ladies and gentlemen. Now we're just Well, now we're just going over the mathematics. No slip. This is going to be my boundary condition 1. My boundary condition 2 is going to be at r equals 0. Now at r equals 0, the value of my derivative, let me rewrite that in a more formal notation, the derivative evaluated at the center line is going to be 0. And what's the reasoning for that? I'm just going to write it here. The symmetry argument. What is the symmetry argument? We're going to go over that in a separate video dedicated only to Hagen-Poiseuille flow. My bad. Symmetry argument. All right. And another textbooks, like I'm following Bird, Stewart, and Lightfoot, but in some other textbooks, they're going to say the reasoning that they're going to present is that velocity has to be finite. Velocity has to be finite. What does that mean? Well, those are topics for discussion in a separate video. All right. And yeah, just before we move forward, we're going to have I'm going to teach you some terminologies regarding boundary value problems. This right here is oops, sorry, my tablet is a little wacky at times, you know that? It's a Dirichlet boundary condition. And this right here is a Neumann boundary condition. So for those of you who want to do an advanced study in this subject, especially in boundary value problems, these names are going to pop up. But for you undergraduate boys and gals and people of other genders, this is not going to be an issue. So this is for advanced study. Okay, and I'm going to link some resources in the description, hopefully. So with that said, now I can finally integrate this. Let me copy that for you guys. All right. So copy that, paste it down. Sorry about that. Sorry about the mess. Hopefully this is not getting too confusing. And let me just zoom out a little so you guys have a better picture of what's going on. Okay. So now I have my boundary conditions. And hopefully I remember some integral calculus. Hopefully I remember that. So otherwise I'm going to be very embarrassed in front of you guys. So now I'm just gonna, by the way, the right hand side, this is all a bunch of constants, so I'm not gonna worry about those. These are all constants, okay? The only variables are radius r, and the axial velocity v sub z. So upon integration, I'm gonna skip some steps real quick and get this result. I've integrated once, and this is the result that I'm gonna get. All right. Now, all right, I have my first constant of integration. And now you can see that I have my derivative term, so it is better to use my boundary condition 2, to use this boundary condition. It is better to use boundary condition 2 at this stage, because the left-hand side is just going to be 0 multiplied by 0. And the right hand side is going to be, as you guess it, there's an r term here. This is going to go to 0 plus c1. Boom, boom. Wow, c1 is equal to 0. Wow, all right. We have our first constant of integration evaluated. Give yourself a pat on the back. And now we're going to move forward. All right, next up. dvz. All right, let me just... Okay, so this is just going to be equal to the negative pressure drop to mu. This is delta P is the pressure drop, L is the length of the pipe, by the way, mu is the viscosity. All right, for those of you who are curious. And now we're going to integrate one more time to get Vz. This is my velocity profile. Negative delta P over 4 mu L times R squared. Time to use my boundary condition 1. Time to use boundary condition 1. Oh, I made the mistake. Damn it, I missed the constant of integration. I did catch it though. You guys did not see that. All right, proceed. Use boundary condition 1. Okay, so I know my boundary conditions 1 says that at r equals 0, the fluid is not moving, no slip, no slip. We're going to talk more about no slip in the upcoming videos, don't worry. So this means that the left side goes to 0, the right side becomes equal to, and yeah, R is now at, R is equal to R pipe. My bad. I am not a professor, I am just an amateur with a tablet. Don't forget that. Alright, R pipe squared divided by 4 mu L plus C2. Turns out C2, I have the value of C2. And by performing simple algebra, I get delta P, pressure drop divided by viscosity times the length of the pipe multiplied by the radius of the pipe, squared. Now if I want a complete solution, I have evaluated my constant C1 and C2, and most transport phenomena professors are happy if you give them this. But some of you are not going to have such forgiving professors, I know. So we're just gonna rearrange this, make it nice and smooth. Let me zoom out a teeny tiny more. V sub z. Now, alright, I'm trusting my instincts. It's been a hot minute since I've done algebra. Alright, so this is gonna become, if I factor out this term, delta P over 4 mu L. I hope I'm not gonna make that big of a mistake. This becomes equal to R pipe squared minus the radius, the radial distance from the center of the pipe. Okay, this one is a constant. This one is a constant, and this one is my independent variable. Just so that we have the terminologies and we have the semantics and we have every the tiny details correct. All right, and this right here is also a these are the parameters. Okay, these are the parameters for flow. These are lumped, these are parameters botched together into a single constant. So now you would know what this expression is telling you, that the axial velocity in a pipe, horizontal pipe, in a horizontal pipe, okay, is gonna be is actually gonna depend on how much pressure drop you have per length, the viscosity of the fluid, and the radius of the pipe. And also, to be precise, if you want the local velocity at a certain distance from the center line, you can get that. Okay, hopefully this is not too much information. All right, so now just to give you a quick recap, this problem was a discussion of a very commonly encountered problem in momentum transfer. Momentum transfer is just a fancy name for fluid mechanics. Do not forget that. The governing equation, this actually is a simplification of the Navier-Stokes. This is the simplification of Navier-Stokes, NS. Okay, don't forget. This is gonna become very helpful in the upcoming videos. A second order differential equation, ODE. The variation is with respect to the radial distance, the radius from the central line of the pipe. You have to integrate twice. Okay, integrating twice gives two constants of integration, hence we're gonna need our two boundary conditions, and these are the two boundary conditions that describe our problem, that describe our physical problem. We haven't discussed the physics so much. We've just my focus has been on the mathematics. So now this right here is just me grinding through the mathematics, solving for my constants of integration to give you the final result. All right, bravo, voila. Maybe one day I'll have a drum roll. Maybe I'll have a little drum roll in the future videos, but for now, it is what it is. Thank you so much for watching. All right, thank you.